A proposed cantilever beam 3 meters long is to be built into a concrete wall supporting characteristic dead and imposed loads of 150 and 80 kilonewtons respectively. Select a suitable UB section in grade S 275 steel to satisfy shear, bending and deflection. So solution, we have to find the shear force, which is also equals to our W or our load. So the formula is 1.4 GK plus 1.6 QK. What we are doing there, we are just factoring the loads. So this is equals to 1.4 times our GK will be this one, 150, and then plus 1.6 times 80. If you add all this, you will get 338 kilonewtons. Now let's find the moment capacity, which is WL over 2. So as you can see, this is a cantilever, so we'll use WL over 2. If it was simply supported, we could have used WL squared over 8. Yeah, so this one, or if it was a cantilever, yeah, like that. This is the formula. So our W, it is this one, 338 times 3 meters divided by 2, we get 507 kilonewtons meters. We can just sketch these diagrams, the shear force and bending diagram. It will look like this. This is our shear force diagram. For the bending moment diagram, it will look like this. It will not be straight. There we'll just use a free hand. That is our bending moment diagram. Now let's select the section. We just do the selection. Selection of the section. This one we do it, we select the section from the table after calculating the area of this section. So is equals to MC over PY. That means that 507 times 10 raised to power 6 divided by, we will assume, when we are first calculating we are trying to select the section, we first assume it is plastic. So we use PY to be 275. So divide by 275. This one will give us, let me use the calculator. We get this one, but this area it is in millimeters, so we change it into centimeters, divide by 1000, because in the table our units are in centimeters squared. So this gives us 1844 centimeters squared. So this one, we go to the table, it is table 9, table 11 from the steel design. It is table 11. We just select an area that is slightly higher than this one that we have found. So for me, I have the table with me. So I have selected my section. I'll get 5. I'll say use 457 by 191 by 89 joist. Its area is 2010 centimeters squared. So this one I've obtained this one from the table 11. So, and this again, so this table we have the depth of this from the table D we found to be 463.6 millimeters. We have our breadth of the section to be 192. BT ratio is 5.42. I'm just writing all of this down here, but it is not necessary. You can just obtain them from the table. So D over T from the table is 38.5. Our thickness of the flange the web thickness is 10.8 from the table, and then the flange thickness is 17.7. These are all in millimeters. Area, as we know, is 210. Now this is in centimeters squared. And then section modulus Z is 1770 centimeters squared. So those are all that I've obtained from the table. They're in millimeters. So let's classify. Now we have select already. The step one it was to find the shear force and bending moments. Then step 2 is to find the selection. We select our section. Now step 3 is to classify. So section classification. So to classify our section, let's first see compare the our T, which is 17.7 millimeters. So this one it is greater than 16 millimeters. So that means that our PY that we will use will be 265 newtons per millimeters squared. We will not use this one now again, 275. We'll use this one as this, because the thickness, as we have seen, it's greater than 16 millimeters. This is the diameter of our steel. So let's classify this was strength classification. This one was for strength classification. That is for strength classification. Now for the section classification, we have to classify the flange. So for flange, we will see the B over T, which is equals to 5.42. It should be less than 9E. So this value, we have it here up from there. All these are from the table. So let's find E. So E is equals to, this is how we find the E. The formula for finding E should be 275 divided by 265 raised to power half So we find our E. Our E, as you can see here, I've calculated it is 1.02. So if we multiply it by 9, what do we get? Times 9, we get 9.168. So this one is greater than that. 5.42 is less than 9.168. So we will say that the section is plastic. This means that the section is plastic. That's our first classification. We have classified it using this formula. Then secondly, we classify the web. Let's see the web. If I say web and flange and you don't understand, it is, let me sketch it here. Our section looks like this. So this is the web and this is the flange. So if you, as you saw, first we'll take BD. So this B is the breadth. It is the breadth of this one, of the flange, and T is the thickness. It's thickness. Now here we are using D over T. D over T, we have it here, it is 38.5. And again, so this is the actual. So the limited one, it should not exceed 80 E. So we have our E. So E, it is here, it is 1.0, so times 80. So 80 times 1.02, if 81. So again 38.5 is less than 81.6. so that means that it is again, it is our section, our web is class 1, which is plastic. Therefore web is plastic. It is plastic modulus. So that means our whole section is plastic. So we can now continue using the value of the plastic modulus. So let's check for shear. Checking for shear. Shear force should not exceed the shear capacity. So we have the shear force. It was here. It was 338 kilonewtons. This shear force. So 338 kilonewtons should be less than or equals to PV, the shear capacity. We don't have the shear capacity, so we'll calculate it. So the formula for calculating shear capacity is 0.6 times PY, then TD. So here is 0.6 times our PY now we are using should be 265, as I said here. As I said here, after classifying the strength, we found that PY should be 265 throughout the whole section. So that's why I'm using PY as this one here. And then T, we have our T here, and then D, we use this 10.8 and this one. So it is 10.6. Those are from the table, then multiplied it by 463.6. And then all of this, we want to change it into kilonewtons, we'll divide it by 1000. So from the, if we calculate that, we get it is 781.4 kilonewtons. Now let's compare them. 338 kilonewtons, our shear force, it is less than shear capacity of 781.4 kilonewtons. That means that our joist is okay for shear. So we just write here, therefore joist is okay for shear. Let's check the shear type. We want to see if it is high shear or low shear, so that it can help us to get the formulas for calculating the bending. So for the shear type, again, shear force, it should not exceed 0.6 PV. So shear force, we have it, it is 338, and then we can calculate this one. Let me just put it direct. 0.6 times PV is 781.4. It gives us 468, so which is greater than this, 468.84 kilonewtons. So this means that it is a low shear. It is a low shear load. This one is a low shear load. So let's check the shear buckling. So checking for shear buckling, we list the DT, which was 38.5 from these values. DT 38. As we know that buckling it always occurs in the web. That's why we're using the values of the depth of the web and the thickness of the web, this ratio, because the buckling usually occurs on the web. So this one, it should not exceed 70 times E. If it exceeds it, that means it will fail in buckling. So let's, again, we have our E. E was 1.02 times 70 times this 70. We get it is 71. So 71 is greater than this. 38.5 is less than 71.4. This 71. So that means that there's no shear buckling. So it is therefore no shear buckling will occur. So we have found that the shear buckling will not occur in our section. Let's now check for bending. So check for bending. So to check for bending, let's find MC. Let's calculate our MC. Moment capacity. MC stands for moment capacity. So since it is a low shear, we'll use this formula, Py into Sx minus Ps times Sy. This is what we will use. We'll calculate this P and this one. The rest we have them. So let's find P, this P here. P, it is a reduction factor. Let me say reduction factor P, small p, this P. So its formula, it is 2 into shear force divided by shear capacity, and then minus 1, then you square everything. So that means 2 into 338 divided by 781.4 minus 1 squared. So we found it is 0.018. That is our P. So the SY is, this is the plastic modulus. Plastic modulus SY. This one we have to find it also. So its formula, it is just TD squared. It is just the area, TD squared over 4. We have our T, it was 10.6 times our depth 46, 3.6 squared divided by 4. So we find it to be 56,955.144 millimeters squared. Again, we can divide it by 1,000 to get it in, but now we'll just have to use it like this. So let's calculate the MC using this formula now. Py, we have it is 265 into, this one was 210, so change it into centimeters, and then minus P is this one, 0.018 times this value, 569,551.144, and then we'll close the bracket. So all this, it will give us we'll divide it in, we'll change it into kilonewtons per meters. So we'll get 529.93 kilonewtons per meters. Now let's compare this with so MC should be less than or equals to 1.2 PYZ. We use this for if our section is a cantilever or a simply supported. For other members, other beams or supports, we will use 1.5. Like if it is overhanging or these other beams, so we'll use 1.5 instead of 1.2. But this now it is simply supported. It is a cantilever, so we use 1.2 times P YZ. So this one is 1.2 times 265 times Z. Z we have it. Z we got it here. It was here. So times Z. So Z it is in centimeters. We'll change it into millimeters. Times 1,000. So this gives us 562.86 kilonewtons meters. So we compare it with our MC. So MC was 529.93 kilonewtons meters. It is less than this 562.86 kilonewtons meters. So that means that our joist is okay for bending. It will not fail in bending. It is okay for bending. Our beam will not bend, so it will not fail. So let's check for deflection. Let's check for deflection. So we have just assumed we have ignored the self weight of the beam, but otherwise we could have also calculated it. So let's check for the deflection. So the allowable deflection or permissible deflection is equals to span divided by 180 for cantilevers. For simply supported, it is span divided by 360 or 300. So for cantilever, we divided by 180. So our span was 3 meters. Into millimeters, it will be 3000. Divided by 180, we get the permissible deflection. It is 16.67 millimeters. So but the actual deflection that occurred in our beam, that can occur, actual deflection, the formula is WL raised to power 3 divided by 8 EI for a cantilever beam. This is the formula. So let's use the 300. Let's use the imposed loads. The imposed loads in this for deflection, the imposed are 80 kilonewtons. So no, we'll use the factored load, the all of it, 338 kilonewtons, to check for deflection. It is in kilonewtons. Let's change it into newtons. Divided by 1000, then times 3000 raised to power 3 all over 8 times E. So our E will use 205. 205, it is also from the table for this, so we use 205 then multiplied it by 1000. Our E was 205 kilonewtons per millimeters squared. So we change this into by times it 1000, then times I. So our I, we just calculate it, or we obtain it from the table. It is 41,000 times 10 raised to power 4. So all of this, it will give us 13.57 millimeters. So it is less than this one, so it is less than permissible. So that means that our joist is okay for deflection. let's say it is okay. For deflection will not affect this joist. It will be okay. So that is the end.